So we're going to discuss the present value of an ordinary annuity. Let's see what that means. So imagine we need to withdraw $700 at the end of each year for the next 5 years. So at the end of 1 year, we're going to take out $700. At the end of the second year, another $700. End of the third year, another $700, and so on and so forth for 5 years. How much money would you have to place in an account today that paid 3% per year compounded annually? I forgot to put that in the first time. To fund those withdrawals. So overall, we're going to be withdrawing $3,500, but presumably we have to put something less than that in today. And the question is, how much would we have to actually put in today to fund those withdrawals? Okay, so what's going to happen is, so that's today. And then at the end of the first year, we're taking $700 out. Then at the second year, taking $700 out. End of the third year, taking $700 out. End of the fourth year, $700 out. End of the fifth year, $700 out. And I kind of spoiled it a bit, but what are we going to do? We're going to find the present value of each of those withdrawals. So our first withdrawal comes at the end of the first year, so the present value is going to be, as you may or may not recall, the formula for present value is a times 1 plus I to the minus n. So this is a, that was our initial value with the 700. That's the interest was 3%, and to the minus 1. And this one is going to be 2 years worth to the minus 2. Minus 3, minus 4, and minus 5. And by this time, it's gonna, here, I'm not gonna directly calculate them all, but for example, the last one is going to be 700 times 1.03 to the power of negative 5. So for example, for this last one, we only need about $603.83 to fund the $700 withdrawal at the end of the fifth year. So what's going to happen is our total required is going to be the 700 plus, the 700 times 1.03 to the negative 1 plus the 700 times the 1.03 to the negative 2 plus the 700 times 1.03 to the negative 3, etc. And this once again is a geometric series. The A is 700, the R in this case is 1 over 1.03 because we're dividing by that each time. So the formula, we're going to jump right to it this time. So we're going to use the same letters, and it's going to be R is the regular payment or recurring amount or how much you're withdrawing on each time. I is the interest rate per compounding period, N is the number of compounding periods, and P is the present value or the initial equivalent value, and sometimes, most textbooks in fact, write it as PV, which stands for present value. As usual, I have a problem with using 2-letter variables. So I'm going to stick with P, but you could do whatever makes you happy. And this is going to be our formula. So let's now actually apply it to the previous problem. And so we're going to say, okay, so we don't know what the P is. We know the R, we know the I, we know the N. So it's going to be 700 times 1 minus 1.03 to the minus 5, all divided by 0.03. So your calculator may be different on how you calculate these things. It's going to be 1 minus the answer is that, divided by 0.03 is that, times 700 is, and so I have $3,205.795 Or if I was going to prettify that, it would be $3,205.80 because we always round to the nearest penny. Now, how much did we actually withdraw? So over the time, we did it for 5 years. So we actually withdrew 700 times 5. We actually withdrew $3,500, but we only put in $3,205, which means we saved about $295 by putting the money in right away. Okay. Example 2. The payments on a car will be $450 a month at the end of every month for the next 6 years. How much would you have to put in an account today at 6% per year, compounded monthly, to make all of those payments? Cars are expensive. Okay. So what do we got? We know that the regular payment has to be $450 a month. The present value we don't know. The interest is going to be 6% per year, but it's monthly, so we're going to divide by 12, which is going to be 0.5%, which is 0.005. The number of payments, we're going to do this for 6 years, and there's 12 payments per year. And so that's going to give us 72 payments. So if we actually calculate it out, we know that P equals R1 minus 1 plus I to the negative n over I, which is going to be 450 times 1 minus 1 plus I to the minus over 0.005, and I'm upset, of course, because I was supposed to be plugging in numbers there, so we'll do it in the next line. 1 minus 1.005 to the power of negative 72, all divided by 0.005. So 1 minus 1.005 to the power of negative 72 divided by 0.005. So that's going to be 450. I'm going to give a halfway point just so you could make sure that you're typing it into the calculator correctly. So it should be something like that. I'm going to keep all the numbers in there. Times 450. So that is going to give us 27,152.7812. Or if I was going to round it to, if I was going to prettify it, it would be $27,152.78. And so that's how much money I would have to put in that account today to fund all those payments. We're going to need to keep that number for part B. How much money would you save by putting the money in today instead of just making the payments as they come? So if you make the payments as they come, it's going to be, we're paying $450 a month, and we're doing it for 72 months. So it's going to be 450 times 72. So we're actually going to give the car company $32,400. But we only have to put that much in the account today to fund all those payments. Which means if we subtract this, subtract this from that one, we get 32,400 minus 2.78. So if we put the money in today, we would save $5,247.22. Which means as usual, if you have a lot of money to begin with, you get even more money.